Here's a problem that all the stuff we did before with constant acceleration won't work because, well, here's what's given. We have a 10 kilogram car on wheels, so there's no friction or anything. But our force is now a function of time. The force changes with time. And that means that the acceleration will change with time. So we need another technique to figure out and answer these questions. But now here is the force function. Here's force as a function of time. So if we know what the force as a function of time is, we got a shot at solving some things. Here's this, and it goes up to 10 at 3 seconds, and then it goes back down to 0 after 5 seconds. So I want to know what is the change in momentum of this system, and what is the final velocity. And I gave you a hint. You need to use the impulse momentum theorem, which says the product of force and time is equal to the change in momentum on the object. Well, if you look at this, if you say, well, whenever you have a quantity here, change of momentum, that is the product of two other quantities, you can always figure out what this quantity is by graphing this as a function of this. The first quantity is a function of the second quantity, and looking at the area underneath the graph. And here we have two triangles. So we'll just figure out, see the area underneath that graph is equal to 1/2 the base, and the base here for this first triangle is 3 seconds. So that's time times the height, which is 10 newtons. And then we're going to add to that the area of this second triangle, which is 1/2 of 2 seconds times 10 newtons. That's the height of this triangle, 1/2 base times height. So the area underneath here is, well, let's see, 3 times 10 is 30, divided by 2 is 15. 15, and we have newtons times seconds. Plus, and then 1/2 cancels the 2, we have 10 newtons times seconds. So the area underneath here is 25 newtons times seconds. Now this is an impulse. This is a product of force times time. And you get newton seconds. But the impulse momentum theorem says that that force times time, as long as it's the net force that's doing this, is equal to the change in momentum of the object. So, so delta P is going to be equal to 25. Now a newton second, what is a newton? A newton is a kilogram meter per second squared. And then you multiply that times a second. Notice that the seconds will cancel. You'll get kilograms times meters per second. Mass times velocity. So there's my answer for part A. Okay. Any questions? Now this is equal to the change in momentum, which is going to be the mass. It's the mass of this doesn't change. It's 10 kilograms the whole time. It's mass times the change in velocity. But that change in velocity is, well, we'll just go mass times V final minus V initial. But what is V initial in this problem? What do we say the initial velocity was? Well, up here we called it V sub 0, but that's the initial velocity is 0. So here's my final velocity right here. So all I have to do to find it is divide the change of momentum by the mass. So the final velocity is going to be equal to the change in momentum over the mass. And that change in momentum is 25 kilogram meters per second divided by the mass, which is 10 kilograms. So the final velocity is going to be 2.5 meters per second. So here's what's cool about this, that even, let me zoom out, and I was trying to save paper here, so I use the same paper we used to get our notebook set up with. And so the moral of the story is this: if I have a force function that varies with time, I can still figure out what the final velocity is by using the impulse momentum theorem, which says, hey, the change of momentum of my object is going to be equal to the impulse, and the impulse is just the product of force times time. Now here the force is a function of time, so I have to graph it and look at the area underneath it to get that product. There's a name for that, by the way, graphing it and figuring out the area underneath it. It's called integration, which we've talked about before and you learn about in your calculus classes. Once we figure out the area underneath it, that's equal to the change in momentum. And then if I know the mass, I can figure out the change in velocity. And if I know the initial velocity, I can figure out my final velocity. Used all the time. Now, by the way, this idea of the force being a function of time, that's way more common in the real world than the kind of stuff we've been doing where the forces are constant. I mean, think about a baseball bat hitting a ball. Is the force constant while it's in contact with the ball? No, no way. It starts off when it's when the ball is first touching the bat. There's hardly any force at all, but it quickly ramps up to a very high force and then ramps down to zero as the ball rebounds. So we have tools and tricks where we can figure out what that force as a function of time is, and then we can figure out the change in momentum of things and all that. So this is this is a very nice problem-solving technique using the impulse momentum theorem. That is all.